Hi. Last week we did a video on defeating microwave weapons, how to defend yourself in a high-powered microwave beam. We got a huge number of questions and comments based on that video, and so today I'm going to address some of those comments, I'm going to answer some of the questions, and then I'm going to demonstrate some additional materials that you can use to protect yourself from microwaves, as well as methods of detecting whether or not you're in a microwave beam. Now, the first thing I was asked to address is the fact that the machine that we're using to generate the microwaves for these demonstrations is dangerous, and indeed it is dangerous. Low-powered microwaves are not dangerous. We're surrounded, we're bathed in high-frequency radiation all the time, from cell phones to baby monitors to wireless systems. But those frequencies will not ionize your DNA, they will not cook you. However, high-powered microwaves are dangerous. I mean, that's why they make them into weapons. Duh. It's also why they have safety interlocks on microwave ovens so that you don't operate them with the door open. But even though microwaves in high energies are dangerous, the voltages used to drive the machine are potentially deadly. There are many areas of this device where you could easily contact over 4,000 volts at relatively high currents. They can be deadly. And in addition to that, there is a capacitor inside of there that will store energy, so that even after you've unplugged the unit, it will retain a dangerous level of charge for some time. Now, the capacitor used in microwave ovens is a little unusual in that it includes an internal dump resistor, effectively converting that high voltage charge into heat, rendering this thing safe within a few tens of seconds and certainly less than a minute. But that is the exception, not the rule. Most high voltage capacitors do not have that feature and can retain deadly levels of electrical charge for long periods of time. You got to be careful. In addition, the cavity magnetron also can be hazardous. If you look at the little stub antenna that's coming out of the end that radiates the beams of microwave out of the end of that cavity magnetron tube, you'll see right near the base of that antenna a little pink ceramic ring. That is made up of beryllium oxide, and if it's intact, it's relatively safe. But if you abrade it, or you break it, or God forbid you machine it, you can generate particles and dust, and if you inhale that or you ingest that, it's extremely toxic. So you want to be careful when you're manhandling one of these devices. Bottom line is, this is dangerous, and if you're not comfortable with dealing with the high voltages or the electric circuitry, don't do this. Or at least find somebody who is competent to do this to shepherd you through the process of building something like this. The point of these videos is to keep you safe, so we don't want to endanger you with the equipment. So now let's move on to the testing. Now, keeping in mind safety, we did not include a switch on this so that we would have a visible means of determining if it's on or off. It's just another little safety backup. I'm going to plug this in, and then we're going to show that this is in fact producing microwave radiation by making this fluorescent tube glow. You can see not only does it glow very intensely in the beam, but you can also see that it diverges very rapidly. So the intensity is very high near the horn, but it spreads out very quickly before it reflects off the metal door. This is important because a number of people commented on the fact that our little device is nowhere near as powerful as a weaponized microwave system. That's true, but in fact that's probably not relevant to the testing because we're putting out 1,200 watts of power out of the end of this horn, and that equates to about 20 kilowatts per square meter. All electromagnetic radiation diverges. It's just a physical fact. And in addition, if you're using a microwave weapon as sort of a crowd control device, you're going to be spreading the radiation out over many square meters. So for a weaponized system to be able to match even the power level of this, it would have to be extraordinarily powerful. So this is probably within an order of magnitude of the same intensity levels of a weaponized system. So now that we've got this thing ready to go, let's see if we can block the radiation with a variety of different materials. Now you can see that this obviously glows like this. Let's see what happens if we put a piece of wood, 3/4 inch plywood, in front of the beam, like this. Now you can see that it glows, and you can see that it still glows. The wood does not block the radiation. Now wood contains water, and water as a dipole molecule will actually flip in the electromagnetic field and absorb some of the energy. It will attenuate the beam, but there isn't a lot of water in plywood. And even though a high frequency, millimeter wavelength weaponized system will be even more attenuated by water, the fact that this doesn't work at all at this wavelength, probably not a good way to protect yourself. Now another option is this material. It's the same stuff we built the poster board out of. It's a corrugated plastic material that's often used as a waterproof alternative to cardboard. And if we make the tube glow like this and place this in the beam, it doesn't do anything. Now, if we replace that with a very heavy piece of fiberglass, this material is so strong, it's an epoxy fiberglass composite, that it will stop a number of different calibers of bullet. But you can see that it doesn't stop the microwaves. The reason none of these materials block the microwaves is because, other than the example with water, which has a polar molecule that can flip back and forth and convert the energy into heat, none of these other materials include any kind of free polar molecules that can interact with the beam. And because they are not electrically conductive, they will not reflect the beam either. It will transmit right through them. So what happens if we get something that is electrically conductive? See that we get the glow, and we also get the glow. As you can see, the Kevlar does not block the radiation. And the reason that is because in the example with the wood, we had a little bit of a polar molecule which is able to attenuate the radiation by interacting with it and absorbing some of it and converting it to heat. But in all of these other examples, these materials do not contain freely mobile polar molecules. They can't interact with the microwaves, and therefore they don't attenuate it. And because none of these materials are electrically conductive, they won't reflect the energy either. You need an electrically conductive material in order to reflect an electromagnetic radiation like microwaves. So let's see what happens if we change gears. Okay, this is called ribbon toe carbon fiber cloth. The reason they call it ribbon toe is they've flattened out the individual little yarns in order to make the material extremely thin and decrease the sort of zigzag of the fibers. This makes this material extremely stiff and extremely strong, and is often used in aerospace applications and very high-end sporting equipment. The bottom line, though, is it's carbon fiber, and even though it's only 250 microns thick, it's electrically conductive. So let's see what happens. Now, as you can see, the beam in front, but nothing in back. In front, but nothing in back. And in fact, nothing over here, but you can see it's reflecting over there. And that's because this is an electrically conductive medium. This material is graphite film. It's also 250 microns thick, and it's formed from hydrostatically pressed graphite. It's often used as a heat spreader in electronic equipment as well as high temperature gaskets in furnaces. It's also an excellent material for exfoliating graphene, as we'll show you in a future video. But the bottom line is this stuff is inexpensive, it's very flexible, it's soft, and it's electrically conductive. Now, once again, glows, but it doesn't. It glows, but it doesn't. And as you can see, it reflects the energy because it's electrically conductive. Now, a lot of people asked us whether or not there would be a way for them to protect a room, either in a home or an apartment, from electromagnetic radiation, including microwaves. And there actually is a good way to do that, taking advantage of the idea that a conductive layer, electrically conductive layer, will block the microwaves and other radio waves. So what you can do is you can purchase this material. We use this in a lot of our projects. It's rigid polyurethane foam insulation. And you can get it in huge sheets at big box stores. It's inexpensive. And it has a thermally conductive barrier in the polyurethane foam. But to enhance its thermal barrier effect, it has a sheet of aluminum on one surface that acts to reflect thermal infrared, increasing the insulation properties. But the aluminum is electrically conductive. So let's see what happens with this in a microwave beam. All right, let's see what we got. A lot of power, no power. A lot of power, no power. And it reflects. If you look, because of the angle, there's very little over here. But as you can see, it's reflecting the beam out this way. And nothing. And power. So this is a very effective means of blocking electromagnetic radiation. So the way you would use this material is typically as an insulating barrier. You would cut it into segments that would then be placed between the studs in a stud wall. And the aluminized film will block electromagnetic radiation. But as we demonstrated, the wood won't. So if you're going to try to create a true Faraday cage, surround yourself with an electrically conductive material, you're going to want to wrap something around this, either a little piece of sheet metal or some aluminum, or you may be in a building that has aluminum studs. But you always want to keep a complete barrier, either always in front of the studs, always completely behind the studs, or you're going to want to wrap this thing up. Also, don't forget the ceiling and don't forget the floor. In any case, we also want to try to find a way to protect you if you're mobile and you're not just building a building. And let me show you how we might be able to do that. So based on electrical conductivity, we had a large number of people commenting and questioning whether or not we could use something like this, an emergency blanket, often called a space blanket or a thermal blanket, as a means of protecting ourselves. It'd be wonderful because it's nice and light, portable, and inexpensive. Question is, does it work? Now this material is based on an extremely thin layer of a polyester film, great insulator, very strong plastic, on top of which they've placed a chemically vapor deposited layer of a few atoms of aluminum. And as a result, the material is electrically conductive. Now if you look at the meter right now, this shows you when you've got electrical conductivity. If I touch these two probes to the surface, you can see that it's electrically conductive. However, if I turn the surface upside down and we do the same test on the back side, it's not electrically conductive. So the aluminum coating is placed only on one surface. So we're going to turn it back over like this. Once again, just to prove it, we have electrical conductivity. And what I'm going to do is I'm going to label this side front. And I'll explain why I did that. Is that spelled right?
Yeah.
Okay. Don't.
Oh, I
Don't.
have to. I don't
Okay.
have to.
No.
I don't have to, but
If
as
you.
long as it's an O, right?
Yeah.
Yeah.
Okay.
So that is right.
That will be actually funny. You got to put that. Is that spelled right? Front. You know.
Yeah. No. Yeah. I'll decide if it's funny.
All right. So let's go ahead and install that in front of the projector and see if this will block the radiation. Now, just like before, we have microwaves in front, but nothing in back. In front, nothing in back. In front, it's getting down through the table, but not behind the barrier. And you can see that it effectively reflects the energy because of the angle of the panel. So this stuff really works. And what's nice is it's light, it's inexpensive, you can carry this around in a pocket. You feel the burning or you detect that you've got microwave radiation hitting you. All you have to do is take this stuff out, wrap yourself up like a hot pocket, and you're good to go. Maybe. Let me show you something. Now, another option is to use a more robust material than the very lightweight space blankets, and that's to use an electrically conductive cloth. They're made in a variety of different formats, but basically what they consist of is an embedded mesh of a conductive wire, in this case very fine copper wires that are embedded in a plastic cloth. The spacing between the fibers is down around 50 microns, so they will stop extremely high frequency, extremely short wavelength radiation. In addition, this stuff is launderable, it's sewable, you can sew it, and it's nice and strong. So let's see if this material will block the radiation. Let's see if it blocks the radiation. A lot of intensity here, nothing here. It also reflects the energy a little bit on this side, not much, but a great deal over here because of the angle that we've got this panel set at. But it blocks the radiation. What's nice about this is this material can be sewn. You could make it into a garment. You could line a jacket with this or a hat, and you'd have something that would last a long time. A neat application would be to actually form this material into a cloak. You could seal it at the throat with a brooch, and you could walk around with your sword, and you could do the I am Luke kind of activity, or Aragorn, son of Arathorn. You could hold this up, you could detect the radiation, tell everybody to get behind you, and you'd be the life of the party. So kind of a neat way to apply this, and it would actually work. So kind of a fun way to use technology against technology. The problem is, if you're walking around in a crowd with one of these tubes, you're probably going to get it broken. It's fragile, it's large, and that's one of the problems of using this out in the open rather than in a lab. So let me show you how we dealt with that. So we got a lot of suggestions or questions from people as to whether or not we could develop a method of detecting the beam that's a little bit better than carrying around a fluorescent tube. And I think I came up with a pretty good solution. This is our old polycarbonate riot shield that has an aluminum grid on the front of it that blocks the microwave radiation. And as you'll notice, I'm walking right in front of the 1200 watt beam. And as you can see on the front, we have these little detectors that are going off based on being hit by the beam. It works. Now the suggestion was made that we should use LEDs, maybe take advantage of the electric field that's built up in the conductive layer in order to drive an LED detector. The reason I stayed away from that is because LEDs pose a couple of challenges there. First of all, an LED wants to run on polarized output, either continuous wave or pulsed DC, and this is generating an AC current. In addition, LEDs have a rather narrow voltage range of operation. Too low, they don't work, and not much higher, and you damage them. So because of that, I decided instead to use neon bulbs. These are little neon indicator lights. The same thing you put on the front of an instrument that you could hook up to AC in order to show that the power is on. What's nice about these things is they're super robust. These could be blasted with 10,000 volts and they'll still continue to work. In addition to that, they work on AC, and these devices do not require any kind of controlling electronics because the tiny little leads that extend out of the bottom that you'd normally hook up to a power supply act as antenna. So you don't need to have any kind of electrical connection to the grid or the material that's blocking the radiation. That's convenient if the grid is buried between, say, 2 layers of poster board, as we demonstrated last week, or if it's embedded in plastic, like the protective cloth. You can't access that voltage. But this gives me an opportunity to talk about a little science. Incandescent bulbs and candles and hot bodies will generate non-polarized light. But almost any kind of electromagnetic radiation generated by man has some degree of polarization because the source is not radially symmetric. There generally tends to be an asymmetry to the source. So the radiation is going to tend to be polarized, with the electric field either going vertically, like this, or horizontally, like this, or some mixture of the two, but there's a tendency for it to be primarily polarized in one direction. When the antenna of these bulbs are lined up with the polarization field, we get a lot of output. But if they're cross-polarized, we don't. Let me demonstrate what's going on there. Now, if you look at this board, I have 4 of these neon indicator lights with their leads lined up with the axis of the bulbs. And if I turn on the device, you can see that only the bulbs that have the leads vertical are producing any kind of glow. Now, if I get it really close, I can cause even the ones with the horizontal axis to glow, because this isn't purely polarized, but there is definitely a preference. And because you don't know if a weaponized system is going to be polarized vertically or horizontally, and it probably will be one way or the other, a cure for that is to simply bend one of the leads at right angles to the other lead. So it's operating a little bit like an inverted V dipole for you radio people. As a consequence, there's always a wire lining up with the field. And now they all interact at the same distance. Pretty neat and very compact. And when you can buy these things for about 50 cents a piece in quantity, it's a great solution. But as you can see, as I get far enough away, eventually they die out. So this can really only detect relatively intense field, just like the fluorescent bulb. And you might think, all right, so what's the point? If it's going to be intense enough a field that I'm going to be able to detect it because I'm getting burning in my skin, does this have any value? And I think it does. Because if you're in a very complex environment, a lot of activity going around, you may be distracted. In addition, you may be in bright sunlight, you may have allergies, you might be exposed to a chemical weapon. Well, nothing is going to make these bulbs go except for the microwaves. So not only would it be a reminder that you might be in a microwave beam, but it's also a great way to document that you've been in a microwave beam for future reference. If you want more sensitivity, there's a way to do that, though, and let me show you that now. Now this is a field strength meter. It's used by radio technicians in order to determine polarity as well as the energy or the amount of intensity you have in radio frequency emissions. It's really nice because it also gives you the amount of power being generated in millivolts or volts per meter. And this is a great method if you wanted to detect or if you're even getting close to any kind of microwave energy. This would work from, a mile away. It would be very effective. The only downside in using a device like this is the fact that it is expensive. They start at a couple $100s and go up from there. So unless you really think you need that extra level of sensitivity, you might not want this. Or if you want to get into radio, it's a great thing to have. It's a great excuse to get a new tool. There is a lower cost alternative that I discovered in doing some of the temperature readings, and that is to use an IR thermometer off-label. Basically not the way that it's designed to be used. You can get these at a big box store for like 20 bucks, so it might be a good solution. Let me show you how these things work and how it operates in this regard. So let's see if it works. We're inside a metal building, so I don't know if this is going to work the way it's supposed to. What this does is it measures the temperature of a surface. And as you can see, this room is pretty cold. It's about 11.7 degrees Celsius. And depending on what you're pointing it at, you'll get slightly different readings just based on the emissivity of the surface. But it's relatively close, 15, 20 degrees Celsius. But watch what happens when we begin to move this toward the microwave device. You can see that the temperatures are getting kind of crazy. There's no way, even though I'm not aiming it even at the device, I'm just aiming it in the general vicinity. I'm getting temperatures of, 90 degrees Celsius above the boiling point of water. So this is a neat method that you can use in order to detect whether or not you've got some microwaves around, and it's inexpensive. The one problem with using a device like this in this format is obviously if you whip this out and you aim this at what you think is a microwave device, you might create a little bit of tension in the people around you. So you might be able to find a device that doesn't have quite the same threatening format, but the idea is the same. It's an inexpensive way to be able to detect if you've got the microwaves at an intensity that doesn't hurt you. So hopefully you found what we've been doing here useful. And I really hope that you never really have to use this information, but the world is getting pretty crazy, and there may be an opportunity at some point for you to look back on this and be able to take this information and help keep yourself safe. And if you like what we're doing here, both with the safety issues that we've covered with microwaves, as well as the broad range of topics that we cover, please consider subscribing to the channel, because the bigger we get, the more YouTube will distribute this information to more people, and that's good for everybody. So I want to thank you very much for watching. You stay safe, take care, and have a wonderful evening.